Hi, I'm Emre, and with my partner Nico, we will be aiming to explain what exactly transistors are, how they work, what they do, and how we practically use them. First off, to clear up exactly what we're talking about, we have to describe what a transistor is so that you could recognize one if you were to see one in real life. This is a picture of a transistor. As you can see, its defining attributes are the three prongs that extend from a black box. These three prongs actually have a distinct purpose in the functioning of the transistor. For a bipolar transistor, these three prongs connect to three semiconductors labeled collector, base, and emitter. A semiconductor is a material that is not a complete conductor or insulator. The most common type of transistor is an NPN transistor, meaning that the three semiconductors used within this transistor are N-type, P-type, and then another N-type semiconductor, respectively. This means that the N-type collector and emitter have extra electrons, making them negative, whereas the P-type base is missing electrons, which can also be referred to as having extra holes in the semiconductor, which makes it appear to be positive. Basically, electrons enter a bipolar transistor at the prong of the device that is the emitter of the transistor. Once an electron is within the emitter, it has two possible routes to exit the device. The first route comes through the center prong of the transistor, which is the base of the transistor. The second course of action would be to travel through the entire transistor and exit the final prong, or the collector of the transistor. However, there are caveats as to where the electron is influenced to go. Electrons cannot cross the base into the collector unless there is a high enough voltage to do so. This is because electrons can easily flow from N-type regions into P-type regions, but a much higher voltage is needed to flow from a P-type region into an N-type region. However, as long as the base voltage is higher than the emitter voltage, the electrons are allowed to flow all of the way through. Here is where the function of a transistor becomes apparent. By manipulating the voltage between the base and the emitter, the current flow from collector to emitter can be controlled. Using this, a transistor can then effectively function as an electronic switch. Electronic switches are used in a variety of applications within circuits. They can differentiate between two different modes of output based off of a given input. This opens the door to a plethora of electronic applications, which is why they are used in most modern integrated circuits. This has led transistors to become what is known as the, quote, brain power behind modern computers. Up to billions of transistors can be used together in order to create incredibly complex and intricate circuits called chips, which are capable of complex logic, computation, and organization of computer memory. The practical and scientific and electronic applications of transistors are arguably endless due to their incredibly versatile nature. However, with the complex application of large quantities of transistors, it is essential to understand the basic physics concepts behind how an individual transistor works to affect an integrated circuit in which it is included.
So we're going to do some math here and design a circuit to show how an individual transistor would work. So to design this circuit, we're going to have to make a couple of key assumptions, which will make designing it much simpler. So the first thing is that the activation voltage of the LED we're going to assume to be approximately 2 volts, because that is about the standard for normal LEDs, and I don't have access to the datasheet for the LEDs that I have. Another assumption we'll have to make along with that is that the activation current of the LED is going to be 15 milliamps, because the average for these kind of LEDs is about 10 milliamps to 20 milliamps, so to be safe, we're going to go right in the middle. And the last key assumption we're going to make here is that the transistor has negligible resistance. And what that means is we're going to assume that there is no voltage drop and no change in current due to the transistor, which for an ideal transistor would be true, so we're going to assume that. Now, there's a couple of equations we're going to need to analyze this, and that is, of course, delta V equals IR, which you can then rearrange into R equals delta V over I, and I equals delta V over R. So now we can start to calculate the voltages and the resistances that we're going to need to put in the circuit to get this done, basically. So the battery we're going to be using is 9 volts, and we're going to be having 2 LEDs in that circuit, which I will show in a second. So that'll be 9 volts minus 4 volts equals 5 volts. So we're going to have 5 volts left, which we're going to need to catch with a resistor, and we can do that calculating the resistance that we're going to need with that, with R equals delta V over I. So R equals 5 volts over 15 milliamps, which is approximately 333 and a third ohms, which the resistor that I have that's closest to that is 330 ohms, so that's what we'll be using for the circuit. And one more thing we're going to have to check is the current that we're going to be putting through the transistor side of the circuit. So the maximum current that can go into the transistor that we have is 200 milliamps. And so just to be safe, we can go with a 1000 ohm resistor, which will also be safer for the LED. So if we do that, 9 volts over 1000 ohms, that's I, we'll get about 9 milliamps. So that's perfectly safe. So now what we're going to have to do is we're going to design the actual circuit part of this. So there's going to be 2 main loops in this circuit. The first main loop, we are going to have our 9-volt battery, and that will be connected with a switch, which we're going to use a push button for, into our resistor that we just calculated to be 330 ohms. And this will have 2 major parts here. The green LED, which will go into a gap, which I'll show for in a second, and a red LED, which we are differentiating the colors here to differentiate the different sides of the circuit. So for now, we can assume that this gap is just closed by a wire, and if we turn the switch on, this current will flow through, it'll go through both of these, and it will be a closed circuit, and both LEDs will light up. So the main component of this, then, is the other side of the circuit, which is going to be the transistor side. So for that, we're going to connect another 9-volt battery into a switch so we can turn it on and off. And in that, we are going to put our other resistor, which is going to be 1000 ohms. And the main part here is going to be a transistor. So we are using an NPN bipolar transistor here, and we can draw those connections like so. Okay, so now what we have is we have 2 separate loops here. So ignoring the transistor, we have one loop here, which will go through both of these, and then this loop here, which will just go through the red LED. So in theory, while this switch is on, this will act as an open switch, and this current will not flow, so neither LED will turn on. If this one is the only one on, it will flow through here freely from the base here to the emitter here, and turn on just the red LED. But then if we have both circuits closed, we have a current flowing through here, current flowing through here, and the base to emitter voltage here will enable the electrons to flow from the emitter to the collector, so current will flow through here, and both LEDs will turn on. So we are going to go see that in the physical circuit now.
Okay, so now we have the actual physical circuit. So we have our two loops here. The first loop is from this battery. It'll go through this switch, the 330 ohm resistor, and both the LED through the transistor, the other LED, and back to the battery. Then the other loop of the circuit, it will go through this switch, the 1000 ohm resistor, the base of the transistor, through the red LED, back to the battery. So what we notice first off, we turn this on, and we have the red LED flashing because the current is flowing from the base through the emitter through the red LED. And then if we try to turn on this loop, nothing happens because the transistor acts as an open switch. So what we can then do, turn this on, turn the other switch on, and the current flows all the way through from collector to emitter thanks to the semiconductors, and the circuit is complete.